Our next presenter is Ariel Kellison from Cornell University. Her field is computer science, and she did her practicum at Sandia National Laboratories. And today she'll be presenting on Numerical Fuzz, a type system for rounding error analysis.
Thank you. So this talk is a little bit different. It's about designing programming languages that are useful for practitioners of computational science. And in particular, it's about a functional programming language called Numerical Fuzz, featuring a type system for rounding error analysis. It's particularly useful for understanding the behavior of programs that evaluate floating point expressions. So the purpose of a rounding error analysis is to derive an a priori bound on the effects of floating point rounding errors on an algorithm. And these types of analyses are fundamental to high-performance computing because they give us a rigorous way to answer the following question of when can we safely trade accuracy for performance. But these types of analyses are challenging to do in practice. They're made complicated by the fact that at this point, we have many different floating point formats to choose from. We also have many different numerical libraries with different dependencies, and each of these different libraries have different accuracy requirements. Moreover, there's a problem here, which is that few tools for automated rounding error analysis exists for practitioners to use in practice. So this leads to the following problem statement that's the main topic of this talk, which is that sound tools that automatically bound rounding errors give pessimistic bounds and scale poorly. So this problem statement requires some explanation, I think. By sound tools, I mean tools that are guaranteed in a very rigorous way to always return a computed error that's an upper bound to the true rounding error produced by an algorithm or a program. By pessimistic bounds, I mean that these tools can provide us with the following bound, that your true error is upper bounded by infinity. And this is not really a practically useful result, although it is always true. And by scaling poorly, I mean that these tools only work on on benchmarks and programs with fewer than 100 floating point operations. So this is really far from what we need in HPC applications. So we can see an example of this problem in practice in polynomial evaluation. So in polynomial evaluation, we're given a value for the variable of the polynomial, and we're given values for the coefficients of the polynomial, and we're tasked with evaluating the polynomial at these values. Now, a simple algorithm for polynomial evaluation is Horner's scheme, which rearranges the polynomial using nested multiplications and additions in order to reduce the number of operations. We can find an implementation of Horner's scheme in the NumPy polynomial libraries, the polyval function. And I've included a snippet of the documentation for this function on the screen. And we can see in the documentation that indeed the polyval function does evaluate a polynomial at specific values using Horner's scheme. But it also includes the following warning, which I hope you can see all the way in the back. It says that for polynomials of high degree, the values returned by the polyval function may be inaccurate due to rounding errors, and that we should use the function carefully. And I hope if you're writing numerical libraries, you provide documentation that's a little more informative than this. And I also hope that no one in this audience wrote that documentation, but if you did, I apologize for using it as a poor example of documentation. So the question, this brings to mind many questions, right? But the one that's most important for the purposes of this talk is how inaccurate should we expect the results of the polyval function to be? If you're a numerical analyst, you already know this answer, but for like most developers of scientific computing applications, you might have questions, or if you're just a general user of this polyval function, you might have that question too. So if we turn to the literature, we would immediately, to try and answer that question, we'd immediately run into our original problem statement, that existing tools tend to generate pessimistic bounds and they scale really poorly. So in this table, we have the relative error bounds produced by a popular tool from the literature, and it works in some cases really well for other problems, but it does really poorly here. So we have the relative error bounds produced by this tool on benchmarks where Horner's scheme is applied to a second order and a fifth order polynomial. So for example, Horner 2 is a benchmark with only 4 floating point operations. Now, what we would like is for the relative error bounds produced by this tool to meet these target, worst-case theoretical relative error bounds that we'd get if we opened up any numerical analysis textbook and input the necessary parameters. But we can see that even for this really small benchmark, this tool produces a result that's 5 orders of magnitude larger than the target. Okay? So this is our starting baseline point. I think we can make progress, right? And that's what we did. So our contribution is Numerical Fuzz. It's a functional programming language featuring a linear type system for rounding error analysis. And it has 3 main useful properties, that it's sound, it's useful, and it's fast. So How does it work? It combines two key ingredients: a graded effect system for tracking rounding errors, and a sensitivity type system for tracking function sensitivity. So let's take a moment to first look at this graded effect system. To understand how our graded effect system works, you have to understand that in functional programming languages, very broadly speaking, functions are total. That means that they're well-defined for every point in their domain. Now, this rules out certain kinds of behaviors for programs that we would expect or want, for example, non-termination, but also handling of exceptions, errors, and input and output from users. Now, these kinds of behaviors in the programming languages literature are what are known as effects. And more specifically, effects are what programs produce during evaluation other than values. So our key idea when developing numerical fuzz was that rounding error actually behaves like a computational effect. And so floating point programs, they produce values, but they also produce rounding error. So we can understand how our graded effect system works at a really high level by looking at this simple function f and its type signature. So this simple function f takes a value of some basic numeric type and produces a value of some basic numeric type. And we can see that by its type signature. But in our graded effect system and in our numerical programming language, f also doesn't produce any rounding error. Okay? So now, for functions that do produce rounding error, using our graded effect system, functions that do produce rounding error, we indicate that by this graded effect annotation on the return type. So this function f in our language is a function that produces a value of numeric type and also at most q rounding error, where q is any constant in the extended positive reals. So it could be infinite, and it can be also any value in the extended positive reals. So how does it work at a high level? Well, we can conceive of a function, any function, and in particular our function f, as executing under two different semantics. An ideal semantics where all of the operations in the body of the function are infinitely precise, and a floating point semantics where all of the operations in the body of the function are finitely precise floating point operations. This value q, this effect grade annotation on the return type of our function, is then the difference between applying f under its floating point and ideal semantics to the same value. And so if you're familiar with rounding error analyses, this is really the local rounding error produced by the function f. But now we need to ask the question of what happens under function composition. So for example, if we have our function f that produces at most q rounding error as indicated by its type and also by shown in the diagram here on the screen, and we have a function g that produces at most r rounding error as indicated by its type and is shown by the diagram of the screen, how do we determine the total rounding error that's produced by the composition of the functions g with f? Well, it turns out we don't yet have enough information to determine this fact. And what we're missing in particular is how g, under its ideal semantics, propagates the local rounding error produced by the function q. And that's where we come to the second component of our functional programming language and its type system, which is a sensitivity type system for tracking function sensitivity. So sensitivity type systems were first introduced in the literature by Reed and Pierce in 2010 as the family of fuzz programming languages, which is where we get the name for our numerical fuzz programming language. But they were introduced in the context of differential privacy, so a completely different field from what we're looking at now. And the key idea in sensitivity type systems is of C sensitivity. And a C-sensitive function is one that amplifies errors by at most a factor of C. And so in this diagram on the screen, we can see that the function f is C-sensitive because it amplifies this small difference in its inputs, this delta x difference in its inputs, by at most a factor of C. Now, in sensitivity type systems, we use the following sensitivity annotation for functions that are C-sensitive in their arguments. And so specifically, this function f that you see here on the screen is C-sensitive in its first argument. And this value c you should think of as any kind of numeric constant. It can be positive, it can be infinity, or any positive extended real number. Okay, so now we can answer our question of what happens under function composition. So if we have our function f that produces at most q rounding error, and we have our function g that we know is k-sensitive and produces at most r rounding error, then the composition of g and f is a function that produces at most r plus k times q rounding error. And in fact, this is a guarantee or main theorem that we've proved about our language, that the relative error of a program is bounded by the value indicated by its type. And this is a soundness guarantee saying that our language always computes relative rounding error bounds that are an upper bound to the true error produced by a program. Okay, so when I first introduced our contribution, I said three things. It was sound, it was useful, and it's fast. So I've talked a little bit about soundness, but I think now we need to see some evidence that it's useful and fast. And we're going to provide this evidence by looking at a few examples of numerical fuzz programs. First, we're going to look at examples of how we can automate analysis using Horner's scheme. Then we're going to look at a language feature for enforcing accuracy of programs. And finally, we're going to look at some evaluation results of our language. Now, I do have a disclaimer that you're going to see some programs that we've written in numerical fuzz here, so please do be prepared to see some code. But I can't really introduce a programming language without a little bit of code. All right, so an example of Horner's scheme. We can write a function, Horner2 FMA, in numerical fuzz. And what this function does is it applies Horner's scheme to a second-order polynomial using a fused multiply-add. And it has two arguments. Its first argument is a variable a that represents the coefficients of our polynomial. And the second argument is this variable x. And now look at the type of our variable x, right? This is our sensitivity annotation, which says that our function Horner2 FMA is too sensitive in its argument. And roughly this corresponds to how many times the variable x is used in the body of the function. Now this isn't always a perfect correspondence in our language, but in this case it actually is. Now, we have implemented a type checker in OCaml for our language. And if we run our type checker on this program, Horner2 FMA, we'll get the following type signature. So our type signature obviously says the types of the input arguments to our function, but it also tells us the type of the return value of our function. And here we have this graded effect annotation, which our type checker infers the error bound for. So here, our type checker tells us that the Horner2 FMA produces at most 4.4 times 10 to the minus 16 rounding error. And this is assuming that all of our constants and variables that are used are binary 64 or double precision. But we can think about writing Horner2 in our language in a different way, where we don't use a fused multiply add in the body of the function, but instead we explicitly use multiplications and additions. And so we probably have more rounding error that occurs because we're not using the FMA. And in fact, if we run our type checker, it will guarantee this fact. So for Horner2 here, not Horner2 FMA, but Horner2 at the top, we see that the rounding error bound that's produced by our language, by our type checker, is twice the rounding error bound that we had for Horner2 FMA. And again, this is inferred automatically by our type checker for our language. So building on these examples, we're going to look at a language feature for enforcing accuracy in numerical fuzz. And in particular, numerical fuzz is a higher order functional programming language. That means that functions in our language can themselves take functions as arguments. And you can see here on this first line that this function, needs accurate, takes a function f as its first argument. And that this function f, if you recall, actually matches the type signature of our Horner2 with an FMA function. So if we were to pass Horner2 FMA as an argument to this needs accurate function, our type checking algorithm would succeed. It would say, yes, you can use Horner2 FMA as an argument to this function. But if instead we were to pass Horner2 without the FMA, with more rounding error, as an argument to our needs accurate function, our type checker would fail with the following error, that it cannot satisfy the constraint that the rounding error produced by that Horner2 function is less than what we require for our function needs accurate. And so at a very high level, we might understand how this enforcement of accuracy within a function could be useful in the development of numerical libraries where we want to test, for example, the effects of using different floating point formats. So now let's look at a few evaluation results. So numerical fuzz scales to very large problems in comparison to what we can find in the literature. And really, it's the only tool to generate relative error bounds at this scale. So here we have benchmarks, increasingly large benchmarks, going all the way up to a matrix multiplication between two 128 by 128 matrices. And although this is not quite the scale of HPC, it's very good in comparison to existing tools. And so this is a total of a little over 4 million floating point operations. Now, what we'd like is our numerical fuzz bound for the relative errors to match these theoretical worst-case relative error bounds from the literature. And we can see that numerical fuzz produces bounds that are at least within an order of magnitude of those. And so this is my claim for our tool being useful. And as far as timing, most of our benchmarks, our type checker can infer the rounding errors in less than 10 seconds, except for this last problem, it takes about 18 minutes. But again, compared to what we can find in the literature, it's very fast. So in summary, our contribution is a functional programming language featuring a linear type system for rounding error analysis. It combines two key ingredients, a graded effect system for tracking rounding errors, and a sensitivity type system for tracking function sensitivity. And there's more in our paper. If you can take a look, we have additional benchmarks, implementation details, ideas for how to handle probabilistic rounding error analyses in our tool, and also how to handle overflow and exceptional values. And that's it. Thank you.